In the second unit, we're going to discuss the expressiveness and limitations of linear classifiers. Let's consider our logistic regression model from the previous lecture. To remind ourselves, the logistic regression model is the model where we have a linear or affine transformation between a weight vector and an input vector x, which returns a scalar that is passed through a sigmoid nonlinearity that squashes the range, the infinite range on the real axis to the range 0 and 1. And this resulting value between 0 and 1 is interpreted as a probability of the input x belonging to class 1. So the question now is, which problems can we solve with such a simple linear classifier? Here again we have the sigmoid function, you can see here, which crosses the value 0.5 at 0. So let's assume now we are in the 2D domain. So we have a 2D logistic regression problem where we have 3 parameters, one for the first and one for the second dimension of W, and then the bias W0. So 3 parameters in total with a 2-dimensional input. The decision boundary of our logistic classifier is exactly at 0, because at 0 this sigmoid function, so 0, x equals 0, so the input of the sigmoid is 0. Because at 0 this logistic function, or the sigmoid function, changes from values that are smaller than 0.5 to values that are larger than 0.5. In other words, if I'm in this on the right half of this space here, the probability that I'm deciding for class 1 is higher than the probability that I'm deciding for class 0. And conversely, if I'm on the left side of this decision boundary, the probability for deciding for class 1 is lower than the probability for deciding for class 0. Because obviously the probability of deciding for class 1, for class 0 is 1 minus the probability of deciding for class 1. And probabilities are bounded by 1, which means that if one, in the binary case, one of these probabilities is larger than 0.5, the other probability must be smaller than 0.5. Right? Okay. That means for our decision boundary of the linear classifier, we have this expression here. Right? X equals 0. This is the decision boundary. So we are basically undecided about the class if x, or W transpose x plus W0 equals exactly 0. Then we're exactly at the decision boundary if this condition here holds. And we decide for class 1 if W transpose x plus W0 is bigger than 0. Right? If we are in this region here, or in other words, if WTx is bigger than minus W0. And we decide for class 0 if W transpose x is smaller than minus W0. Then we are on this side here of our logistic function, where we are having a probability of less than 0.5 of deciding for class 1, which means we're deciding for class 0 with higher probability. Right? Okay. So what you can see here on the right is only the visualization with respect to this sigmoid function. Of course, this decision boundary in x, in like the bold x space, in this 2-dimensional x space, is in a 2-dimensional space, and you will see that later. So we have a line in that space that separates one side from the other side. But of course, this scalar here is then something that we can simply visualize with a 1D plot. Okay, so now let's look at some concrete problems that we can solve with this simple classifier. And let's look at some of the most simple problems that we might want to solve. Some logical Boolean operators. Let's start with the OR operator. Just to remind ourselves, I've put the expression for the classification rule on the top here. So we're deciding for class 1 exactly if the inner product between the weights W and X is bigger than minus W0, the bias term. Okay, so we have a two-dimensional space, we said, which means that we have 4 possible inputs: 0, 0, 0, 1, 1, 0, or 1, 1. And if we consider the OR operation, this is what the output should be. 0 and 0 maps to 0, and if any of the x1 or x2 is 1, we obtain a 1 as an output. This is the simple definition of the logical OR operator. Now the question is, how do we choose our 3 parameters, which are the elements of W and W0, such that we can implement this OR operator with this classifier here? Is it even possible? In other words, what do we need to fill in here for W and for W0, or minus W0 actually, such that this rule correctly separates this class 0 and 1 for this particular binary example? Let's look at an illustration of this problem. So here on the bottom, I've drawn the x1, x2 space, and I've drawn the 4 data points at 0, 0, 0, 1, 1, 0, and 1, 1. And using color, I've indicated which class they belong to. For instance, the data point at 0, 0 belongs to the class 0, and all the other data points belong to class 1. Now the question is, can I find a decision boundary, a linear decision boundary, because we have a linear classifier here. It's a linear equation that separates the red from the green points. And from this visualization, it's very intuitive. Obviously, I can do that, right? I can find a line that separates the red point from the green points. Now the question is, how do I need to choose W and W0? Well, we can set W and W0 by thinking about them for a moment. For instance, what we know is if we have the point 0, 0, if we pass in the point 0, 0 here, which means that the entire expression here becomes 0, this may not be bigger than the value on the right, which means the value on the right must be bigger than 0. So let's choose it as 0.5. If we choose it as 0.5 and we plug in 1, 0, oh, this is this value actually, so 1, 0. So for x1 we have 1, for x2 we have 0. Right? And we choose this vector here as the vector 1 and 1, we obtain a 1 here, which is bigger than 0.5. So these points would be correctly classified. The intuition why I've chosen the vector W as the vector 1, 1 is that I want to find a decision boundary that has a normal into the direction of the diagonal here. So the normal must be something that is proportional to 1, 1. So I've chosen 1, 1 because I know that this decision boundary, the normal of the decision boundary must face into this direction 1, 1. So if I'd chosen 1, 1 and 0.5 as minus W0, I've classified these two correctly. What about the other ones? If I look at this one here, I have 0 and 1. If I look at this one here, I have 0 and 1 for x1 and x2. So I also get 1 here if I have 1 and 1. So I'm also classifying correctly. And if I have both x1 and x2 1, then I get a 2 here, which is also bigger than 0.5. So this is clearly the correct decision rule. By just verifying manually and tuning and tweaking these values manually, just using our intuition. Again, I've chosen this vector here, the normal, as 1, 1, because I know by looking at this plot here that this decision boundary should be oriented that way, and then the only remaining unknown was this value, and I've just chosen it based on trial and error and to separate this and this from this data point here. Right. Okay, so what about other operators? Let's look at the AND operator. You can see an example for the decision table for the AND operator. 0, 0 maps to 0, 0, 1 maps to 0, 1, 0 maps to 0, and only 1 and 1 maps to 1. In other words, we have the situation here where these 3 nodes here are the negative class or class 0, and this is class 1. So how do we need to choose the values now? Well, again, we have a decision boundary, just by looking at it, which has the normal facing into the same direction as before. So we should probably choose 1, 1 here, but a different bias term. So what should the bias be? Well, 0.5 wouldn't be the right bias, because then if I would look at this point here, we have seen it before, this would be classified as class 1. And I have 1 times, well, for this point maybe we have 1 times 1 plus 0 times 1 is 1 is bigger than 0.5. So I need a bias term here that is bigger than 0.5. That's actually bigger than 1. So I choose 1.5. I choose a line that passes through the intercept 1.5. In this case, these 2 points here, for which the scalar product here is 1, because only one of these 2 is 1 and the other is 0, they are both smaller than 0.5. So they are classified correctly as class 0. On the other hand, this point, where we have 1 and 1, the inner product is 2. It's 1 times 1 plus 1 times 1 equals 2. Is bigger than 1.5, so it's classified correctly as class 1. Okay, let's look at yet another example. So here we have the NAND operation. This is the not AND operation. Now, since we already know how the AND operation is defined, it's pretty clear how we have to define the not AND operation, which is just the reverse. You can see here the outcome that was 1 before is 0, and the ones that were 0 before is 1. Or in other words, these 3 points are class 1, and this one here must be classified as class 0. So in this case, the normal is obviously must face into the other direction, right? And also we need to change the sign of the bias term here. So in this case, if we look at some examples, for instance, the example 1, 1 here. Now, if we multiply this with this weight vector, we get -2, and -2 is not bigger than -1.5. It's smaller than -1.5, so it's correctly classified as the negative class. On the other hand, if we set x1 or x2 to 1 and the other one as 0, we get a -1 here, which is bigger than -1.5. So it's correctly classified as class 1. If we have 0 and 0, we get 0 overall, which is also bigger than -1.5. So this point here is also correctly classified as class 1. Okay, so we see that we can represent a whole range of simple logical operations using this simple linear classifier. But now let's look at the more tricky case, the XOR case, the either-or case. The either or operator or XOR operator is defined as mapping only the values that are either 1 and for the other variable 0, or 1 for one variable and the other variable is 0 to 1. So only where we have a difference in the variables we map to 1. If both are the same, we map to 0. If we now plot this expression here on the right hand side visually, we see it becomes much harder now as a decision problem, because we have these two red points that are opposing each other and these two green points that are opposing each other. So it's not obvious how we would find a decision boundary. For instance, if we would look at the decision boundary for the OR operator, we could see that it would correctly classify these 3 points here, but not this 4th point here, because this would be classified as green, as class 1. Similarly, if we would look at the NAND situation, at the NAND operator would correctly classify these 3 points, but not this point. So what should we do? It seems like this is not a problem that we can linearly discriminate. So visually, it's really obvious that the XOR operator is not linearly separable, and this is true. So maybe let's first look into it a bit more formally. Can we actually formally convince ourselves that this is true? Why is the XOR operator not linearly separable? In order to see this, let's step back for a second and just recap for a moment what a convex set is. A set S, so here I have shown 2 sets here in green. A set S is called convex if any line segment connecting 2 points in S lies entirely within the set S. Or more formally, if 2 points x1 and x2 within the set S, then any point that can be expressed as the linear combination of lambda x1 plus 1 minus lambda x2, where lambda is from the interval 0 to 1, must also be in the set S. Or visually, if I consider this set here, and I take these 2 points, then all the points that are in between must also be inside that set. We can already see that the left example is not a convex set. On the other hand, on the right side, if I look at these 2 points, all the points in between are inside the set. And we cannot find any 2 points in that set where this doesn't hold true. So this is a convex set. Okay, so let's recap briefly what our decision regions actually look like. If we go back here, look at one of these decision regions, we see that these decision regions here, so the region where we decide for one class and the region where we decide for the other class, are actually half spaces. Right? They are separating the 2-dimensional plane into halves. They have an infinite extent into these directions here, but they are bounded by this linear decision boundary here. So we have a separation of a 2-dimensional space into 2 half spaces through this decision boundary. And it's clear that a half space is a convex set. There is no 2 points inside a half space here, which is indicated by this gradient, but actually it's reaching into infinity, right? Into each direction in infinity, just bounded by this decision boundary here. It's clear that if I look at any 2 points in that half space, all intermediate points are also inside that half space. That means half spaces are convex sets. Now suppose there was a feasible hypothesis if the positive examples are in the positive half space, then all the points that are in between must be as well, by the definition of a convex set, because a half space is a convex set. So let's say, well, we have these 2 points here of our original XOR example, then all the points in between must also be in the half space, in the green half space that classifies for the class 1. Similarly, the red line must lie entirely within the negative half space. But we can already see that this cannot be, because the intersection point, the point where the red and the green line intersect, cannot lie in both half spaces. So here we have our contradiction. We have found a point that supposedly lies in both the space that is classified as class 0 and the space that is classified as class 1. But that cannot be true, because a point cannot be classified into 2 classes simultaneously. Okay. So now we have convinced ourselves more formally, that this is correct. There's no linear separation of the XOR problem. And I want to complement this view with some historical remarks. And we have seen this already in the first lecture, where we're talking about the history of deep learning, while linear classification showed some really promising results, even for complex image classification problems in the 50s and 60s, for instance, the perceptron, the limitations became clear very soon, as they have been written down in Minsky and Papert's book Perceptrons in 1969 as well. For instance, the XOR problem is a very simple problem, just 4 data points, but it cannot be solved as the model capacity is not enough. The model capacity of a linear classifier is not enough to separate the classes correctly, because the model capacity of a linear classifier is inherently limited to linear decisions. So we can only make linear decisions, not even solve this simple problem correctly. And this led to a decline in interest and research in neural nets in the 70s. But the question, of course, is, well, we want to solve nonlinear problems. It's not enough to just solve linear problems. So what can we do about it? How can we solve nonlinear problems? Well, the first thing we can do is, as we did previously in the case of polynomial line fitting or polynomial curve fitting, where we were using a linear model to fit a nonlinear function, we can again, in this case, consider an extended feature space. In the case of polynomial curve fitting, we were adding monomials as features. Now here we can also add features. For instance, instead of considering the vector x directly, we can consider the vector psi of x, the feature vector, as x concatenated with the product of x1 and x2. So we have the original x1 and x2. This is the original vector x. And now we have concatenated it with x1 times x2. So what does this change? So here on the bottom you can find now the feature table for this situation, where we have the features for each combination of inputs, x1 and x2. It might not be obvious that this helps from this table, but it becomes more obvious if we look at a visual of it. So here on the right, I've drawn again, similarly to the previous 2D examples, but now in 3D. So I hope you can recognize these 3 dimensions here by the unit cube I've sketched in gray. So I've plotted these 4 points here, the feature points, now in three-dimensional space, in this feature space. So for instance, we have this negative point 0, 0, 0, and also 1, 1, 1. And then we have these 2 points 0, 1, 0, and 1, 0, 0, which should be classified to class 1. And now you can already see that in this lifted space, in this higher dimensional feature space, it now becomes suddenly possible to separate these classes. For instance, by this plane. It's of course difficult to draw in 3D, so I did my best here. I hope you can see I draw basically not only the plane, but also the line segments here indicate where the plane intersects the unit cube to better see the plane. You can see that the green points are below the plane and the red points are above the plane. And now we see that even a plane, which is a linear decision boundary just in a three-dimensional space, allows to solve this originally nonlinear classification problem. The classification problem that was nonlinear in 2D space, now in 3D space we can actually solve. And this is analogous to the polynomial curve fitting examples that we've seen in the first lecture, or also to the ideas in support vector machines where we use kernels to lift the feature space. So here's another example to illustrate even more, this is from the deep learning book, that the representation actually matters. If we want to find a decision boundary that separates this blue from the green class here in XY space, it's impossible with a linear classifier. However, if we transform this data set into the R and theta space, which is now in polar coordinates. So R is the radius. So we have a center here, and then we express each point in terms of the radius and its angle. Okay. Now you can see if we have this other, also in this case two-dimensional, is not like a higher dimensional and the original input space it's just another representation. We can see that now suddenly it becomes possible to actually separate the two classes with a linear decision boundary. So the representation of the data really matters, and that's what deep learning is about, to find good representations at intermediate stages of a computation graph, as we will see in the next unit. But of course the question is, well, how to choose the transformation? In this case, we have looked at this data and we've seen that maybe the polar coordinates are a good idea. But this can be very hard in practice. Yet it was the dominant approach until the 2000s, at least in vision and speech, where people manually engineered, for instance, CIF descriptors to describe image regions using histograms of gradients, based on the intuition that this histogram of gradients capture relevant properties and abstract away irrelevant invariances. Now, designing these features by hand is clearly not the best thing you can do, and it turns out that all this, or in most cases, as long as you have enough data you can train from or learn from, it's always better to have an algorithm, a computer, to design the feature spaces for you. And this is what representation learning is about. Instead of hand designing these representations, instead of specifying, well, we want to have polar coordinates, we want to learn this. We want to learn these intermediate levels of our network such that these features emerge that are easy to classify in the end. In other words, now the human doesn't need to choose the correct function anymore, the correct feature representation, which is effectively just a function, but only needs to provide the right function family for the optimizer to optimize in and to retrieve the best function from within that family, right? So instead of designing the function itself, we're going towards designing families of functions. Okay, so let's go back to our XOR problem and what that means for our XOR problem. We haven't solved it yet with the original linear classifiers. We have extended the feature space, but we have used our intuition. It was a little bit like magic. But now, how can we actually do this in a principled way? Well, we have seen that there is a linear decision boundary that does something useful. It's not correct because it doesn't correctly classify the red point, but at least it can separate the red and these two green points. and this is the OR operator. Similarly, we have seen that there is an NAND operator, a not AND operator, that correctly separates these 3 points from each other. And you can already see that by combining these two, I can get a classifier that does the entire classification correctly, which is the XOR. If I combine the OR and the NAND with an AND operation, then I obtain exactly the XOR classifier. Right? In other words, a point like the green points here, they must lie both on this side, on this half space of the OR decision boundary, and they must lie on this side of the NAND decision boundary. And all other points are classified into the class 0. So this is how I can now express the XOR operation using the 3 operations that we've seen before, the AND operation, the OR operation, and the NAND operation. By first calculating the OR operator of x1 and x2, then the NAND operator of x1 and x2, and then combining these two with the AND operation. That's cool, no? So now, what does this mean in terms of a computation graph, in terms of a program? What this effectively means is, because we can express each of these as individually as logistic regressors, is that this above expression here can be rewritten as a program of multiple logistic regressors. So we have one regressor that here's a linear function with a logistic step function, a logistic activation function that represents the OR operator. And then we have this one here for the NAND, and then we combine the OR and the NAND results. So H1 and H2 is then stacked into this vector bold H with the AND operator to yield Y hat, which is our prediction. And I've denoted these two here as H1 and H2 because these are hidden layers. It's actually our first multi-layer perceptron that we're looking at here. These are hidden layers in our computation graph because we have an input X that feeds to some computation nodes, some hidden nodes for which we don't have the observations for. We only have the observations for the output Y or output Y hat. And then these two H's input to Y hat. And for all of them, we have, of course, the parameters here in orange. We have the ones for H1, which are the parameters for the OR operation, the parameters for the NAND operation, and the parameters for the AND operation. So again, note that H is a nonlinear feature of X because we have passed it through this nonlinearity. And we call H a hidden layer. Now we can simplify this computation graph here on the right a little bit by combining these two equations, H1 and H2. As you can see, these are scalar equations, and as before, we can now apply the sigmoid function element-wise to the output of not scalar. This is a scalar expression here, the output. We can also do this on vectors. So we can rewrite the two 1D mappings, H1 and H2, as a single 2D mapping bold H by stacking the W vectors for the OR and the NAND operation and multiplying with the X. So this is now a matrix bold W. And also by stacking the scalar biases WR and WNAND into a vector W. Now we have a matrix vector plus vector operation. And we have an element-wise application of the sigmoid to obtain a two-dimensional vector H. And this is the resulting computation graph here, where we have the input X that feeds to the hidden layer H, and then the output Y hat depends on the hidden layer H. Now, before we have specified all these parameters by hand in order to define the OR and the NAND operation. But of course, we don't know these parameters. But the beauty about specifying this problem using these logistic regressors is that this is now fully differentiable. We don't have non-differentiable step functions here, but we have differentiable sigmoid activation functions, which means that we can start from a random guess for all of the parameters, for the matrix W and the bias vector W, and for W and for W and non-boldface and the bias. So we start with random parameters, and then we optimize for our data set and learn these parameters using gradient descent, where the gradients are computed using the backpropagation algorithm. And this is really our first multi-layer perceptron. It's a multi-layer perceptron because we have two layers here. Each non-input node is a layer in this graph. Each computation node that is not an input is a layer in this graph. So we have one hidden layer and one output layer. Or you can see it also here on the right. We have these two expressions. These are two layers. Both are affine plus sigmoid transformations. Affine and sigmoid transformation.